Okay, what we're going to do in section 7.3 is we're going to start out by discussing some more system solving techniques. We spent lesson 7.1 discussing how to solve a system with two equations with two variables. We can use either elimination or substitution, we know. We can also use a graphing approach as well. But ultimately, what it boils down to is that sometimes that we're going to encounter systems that have more than two equations and more than two variables. Okay, so we're going to look at a couple of techniques here today that will help us to solve a system of three equations with three variables or four equations with four variables. Okay, and then the second half, which we'll discuss when we come back from break, is going to be how do we use matrices to solve systems of equations. Okay, so that's what we're going to ultimately be dealing with here in section 7.3. So the first thing that we're going to tackle today is the solving of systems by using what we call Gaussian elimination. Okay, Gaussian is named after mathematician Gauss. And ultimately, the directions that we're going to see are going to be use Gaussian elimination to either put the system into triangular form or to solve the system. Okay. So changing to triangular form ultimately helps us. It's a starting point for us to solve the system. Once we get it in this triangular form that we speak of, and then we'll be able to use our elimination and substitution techniques to solve the system. So remember, just like before, when we had two equations with two variables, our whole goal here in solving a system is to find the values of the variables that will make both sentences true. Or in our case, make all three sentences true, or all four sentences true, etc. Okay. So this idea of Gaussian elimination, we're going to essentially follow these three steps, and if we can follow these three steps carefully, we should be able to solve really any system that we're given. Okay, provided that it has a solution, of course. So ultimately, the following operations produce an equivalent system of linear equations. Okay, so in other words, when we're dealing with a system of equations, okay, it is okay to do number one, which is interchange any two equations of the system. Okay, so it doesn't matter the order that they're in, we can interchange them as we see fit. Okay, it is also okay to multiply or divide one of the equations by any non-zero real number. Okay, obviously we don't want to multiply an equation by 0, else we wouldn't have an equation anymore. Okay, so it is okay to multiply one of the equations by any non-zero real number. Okay, and then number 3, it's also okay to add a multiple of one equation to any other equation in the system. Okay, so these three steps, okay, are okay for us to use when we're solving a system of equations. Okay, and really, if you think about it, we've done those steps when we did in section 7.1 when we solved by elimination. Okay, we multiplied one or both of the equations by a strategic number so that we could add them together and get a variable to drop out. Okay, so we have some experience with this. We've already been doing that. Okay, so what we're going to look at today really isn't any different than what we've done in the past. Okay, so let's take a look at in your book on page 604. I'm looking at number 6. We're going to take a look at that one. We have x plus y minus 3z equals -1. And the second equation is 2x minus 3y plus z. And that equals 4. And 3x minus 7y plus 5z. And that equals 4 also. Alright, so just to relate this situation to things that we already know, okay, as we talked about and have talked about for several classes now at this point, when we have a system of two equations with two unknowns that are linear like this, okay, we know that that those represent lines. Two equations with y and x, we know that they're two lines. We're trying to figure out where they intersect. Okay, so is there a geometric significance to a system of three equations with three unknowns? And the answer is yes. Okay, we're not going to get into much of the geometry of it in this class, but ultimately these are essentially equations of planes. Okay, So instead of lines, they become planes when we put a third dimension in. Okay, and ultimately these three planes, okay, if we find an intersection point, if we find a set of three numbers that make this true, okay, then that means those planes are going to intersect at one point. So for instance, if you look at this room over here, take the back wall as a plane, the side wall as a plane, and the floor as a plane, okay, all three of those planes would intersect down in that corner there, wouldn't they? Okay? And so that's ultimately what we're finding here is the intersection of three planes. Okay? So it's really exactly the same as what we've been doing. Okay? We're just working with a three-dimensional system instead of a two-dimensional system. Okay? So that's the geometry of it. Now the algebra of it is going to work again almost exactly the same as the algebra that we did for our previous work with two equations with two unknowns. So what we want to try to do here is take any two of these equations. It's totally up to us which two we want to use. Okay? And what we want to try to do is get rid of x. Okay? So this is that Gaussian elimination, as I mentioned. We want to eliminate, okay, the variables as we can get down to, hopefully we can get down to one variable equals something, and then substitute back in and go from there. Alright, so the process is going to be this. I'm going to number these. I'm going to take number 1, 2, and 3. Okay? So I'm going to take numbers 1 and 2, and again, you can do any of the two that you choose. You don't have to do numbers 1 and 2, but I'm going to just pick 1 and 2 just for argument's sake. And I want to eliminate x, so that means that I'm going to take number 1 and I'm going to multiply it by -2 because that's going to put -2 in my x column. So I'm going to do -2x minus 2y plus 6z equals 2. So again, I'm going to take that number 1 and I'm going to multiply it by -2. And I'm going to match that up with number 2 equation. Okay. And then I'm going to go ahead and add those together, and that will eliminate the x's. So I'm going to have -5y plus 7z equals 6. Okay. Alright, so this is another new equation. I'm going to call it number 4. Okay. And I like to number these as I go because that helps me keep track of what's what. Okay. And so that's my number 4. And then what I'm going to do next is I'm going to pick two other equations. I already used 1 and 2. So now I'm either going to use 1 and 3 or I'm going to use 2 and 3. Okay, and I'm going to do the same thing. I'm going to eliminate x. Okay. So again, it's up to you on which you choose. I'm going to go ahead and do numbers 1 and 3. Okay, just because I can multiply by -3 on number 1 and eliminate the x with number 3. So I'm going to go ahead and multiply by -3 this time. And I'm going to have -3x minus 3y plus 9z equals 3. I'm going to match that up with number 3. I'm going to eliminate my x's. That's going to give me -10y plus 14z equals 7. I'm going to call that equation number 5. Okay. Alright, questions so far? So again, you got your choice. Okay, you can use either 1 and 2, 1 and 3, or 2 and 3, and ultimately you're going to pick 2 out of those 3 choices and you're going to eliminate x. Okay, now if you look at equations number 4 and 5, doesn't that look like a system like we're used to? Okay, so guess what we're going to do with 5, 4, and 5? We're going to eliminate either y or z. So I'm going to eliminate, because again, we want to put this, one of our goals is to put this in triangular form. So to do that, we generally want to get rid of x with 2 of the equations and then get rid of y with these 2. So we're going to go ahead and get rid of y. So I'm going to take number 4 and I'm going to multiply it by -2. So if I do that, I'm going to have 10y minus 14z equals -12. I'm going to match that up with number 5. Okay. And in this case, I will have that. All right. And in this particular case, notice what happens. Yeah, they all cancel out, don't they? And we wind up with a 0 equals -5 situation. Okay. And if we have 0 equals -5 situation, okay, doesn't work, does it? Okay. So with that said, when we get down to this point, and if those letters drop out like that, okay, then we're at a point where we're going to have to say that there is how many solutions to this system? Yeah, there's none. Okay. All right. So we're going to do another one because I want to illustrate another situation. But if that's the case, then we can be done here. Now, normally what would happen here if there was a solution, we would wind up with z equals something. Okay. And if z would equal something to finish this problem out, let's just say for argument's sake that z was 5, okay, then we would have our z equals 5. We'd have one of the three answers that we need. Okay, we could take that z and we could plug it into either number 4 or number 5 and find y. True. And then if we knew y and z, then we could put those two into either 1, 2, and 3 and find x. And at that point, we would have all three variables, wouldn't we? Okay. So again, the process is really the same as we did with elimination. Okay, it's a little more involved though because we ultimately have to find 3 variables instead of 2. Okay. All right. Go ahead and look at on your number 3 was the other one I wanted to look at. We have x minus y plus z equals 0. We have 2x minus 3z. And I'm going to put these in columns like this. You'll notice as I write it down, unlike what they wrote in the book. And then the negative x minus y plus 2z, 2z that is, equals negative 1, 2. So we've got a 2z here. All right, now if we're going to solve this system, ultimately if our job is to solve this, okay, one thing to notice is that this one already doesn't have a y in it. Okay, so if we were to be able to take these two, okay, and eliminate the y, okay, we would have one equation, another equation that has an x and a z only. True? So if we take these two, matter of fact, if you look at, if I label these 1, 2, and 3, if I were to add 1 and 3 together right now, okay, the x actually would drop out, wouldn't it? Now, do I really want the x to drop out, though? Remember, what would be nice is if I could let the y drop out, then I could get matched up with number 2, and then get rid of either the x or the z. So the better case here, I'd probably take number 1 and I'd multiply it by negative 1. So that'd be negative x plus y minus z equals 0. Okay. And then match that up with number 3, negative x minus y plus 2z equals negative 1. And if I add those together, I get negative 2x plus z equals negative 1. And I'll call that equation number 4. So, and then I want to match that up with number 2. So if I bring 2x minus 3z equals negative 1. Conveniently, number 2 and number 4 already have an elimination right in front of us here. We don't have to even multiply at all. On this one, we can just add them. And we get negative 2z equals negative 2. And therefore, z would equal 1. Alright, and as mentioned, what we're going to do is take this z and substitute it back into, I would suggest either number 2 or number 4. And in number 2, if we write 2x minus 3 times 1, okay, we could plug that right into number 2 and find x. So we'd have 2x. And if we had minus 3, we'd add 3, so we'd have 2 over here. We'd get x equals 1. And then finally, we can take x and z, and we can put them into either number 1 or number 3, and figure out what y is. Okay. So if I go 1 minus y plus 1 equals 0, that would be 2 minus y equals 0. And of course, if we solve that, we'd have y equals 2. So our claim is that 1, 2, 1, okay, is the solution to this system. Okay, and just like any equation solving process, we should check. So we already know it works in number 1. If we put a 1 in here and a 1 in here, we'd have 2 minus 3, which is negative 1, so it works in the second sentence. Okay. In the third sentence, we'd have negative 1 minus 2 plus 2. So negative 1 minus 2 plus 2 would also equal negative 1. So it did check, so we can walk away knowing that we got the problem correct. Okay, questions on that process?